This is Jack Jackson. Today we're going to be talking about two sample inferences about variances and standard deviations. These are based on an F distribution, so this will be an F test and an F interval. So recall that we used a chi-square distribution for testing for variances or standard deviations of the one sample against some known distribution. And an F distribution is kind of a variation on a chi-square. It's very similar to it. But it turns out if you take the ratio of the two sample variances, you get a statistic called F, which turns out to be following something that we call an F distribution. And this F distribution is actually a family of distributions, and it has two parameters, again, called the degrees of freedom. We have the degrees of freedom 1, which is the degrees of freedom for our first sample, which is 1 less than the sample size for that sample. That's our degrees of freedom for our numerator. And then for our denominator, the degrees of freedom are the sample size for that sample size 2, n sub 2, subtract 1. So 1 less than the sample size. So just like in the chi-square distribution and in the T distributions, the degrees of freedom is 1 less than the sample size, except here we have two samples, so we have two different, possibly, degrees of freedom, two parameters. The PDFs of these distributions are very similar to chi-square distributions. Some of their characteristics are they're completely first quadrant graphs. They're only defined for non-negative inputs, positive inputs, and 0. They start at the origin, 0, 0. They go up to a maximum and then come back down and trail out to an asymptote of 0 on the right. So they're skewed out to the right. And if you go back to Unit 3 on the section called More Continuous Distributions, you might want to go back and review that now. But if you go back to that section, we looked at the graphs of several F distributions. At that point, we didn't talk about where they came from. Now we do. But we did look at the graphs of several PDFs and CDFs for F distributions, and we learned how to use our calculators to compute probabilities and inverse probabilities based on the various F distributions. So here's an example. If we take samples of size 15 and 20 from two normally distributed populations and compute their sample standard deviations, then the ratio of the variances, S standard deviation 1 squared, so that's variance of sample 1, divided by the variance of sample 2, that's distributed by an F distribution with 14 and 19 degrees of freedom. So if we wanted to graph the PDF, we can do this with the built-in function on our TI calculators pretty easily. You go to your y equals screen, clear out everything else, go by the first y1 there. We want to put in FPDF. To get that, you go to distributions, which is second, VARS, to get distributions up at the top, and then just go down till you find it, and you'll find FPDF. Then the inputs are, first is the x value, which is going to be a variable here, and then the 2 degrees of freedom, 14 and then 19. Actually, turns out it doesn't matter whether you put the 14 or the 19 first. It gives you the same graph. And then we choose a window. I'll block that out here, but that should start at 0. And then in this particular one, I went from 0 to 4 on x, and from negative 0.1 to 1 on y, and I got a pretty decent looking graph, and you can see the graph of the PDF there. It's a very similar shape to what we saw on the chi-square graphs. For the CDF, we go to our y equals screen. I cleared out everything else and put FCDF, and FCDF again you get from going to distribution and then find it. I believe it's number 0, I think. And then this one, you give it the lower and upper limits. So the lower limit's going to be 0 and x for the upper, and then your degrees of freedom, 14 and 19. And of course, as with any CDF, it starts at the origin, or starts at 0, in this case at the origin, because there basically is no negative input allowed. So you start at the origin, goes up, and levels off at 1 eventually, actually an asymptote. Now, We also, again, back in Unit 3, we talked about how to take these two pictures and find probabilities either by shading using f function integrate or the numerical integral here, calc whatever it is, 9 or so on the graphing menu, and shade and figure it out here, or by just figuring y values over here on the CDF. And we did inverse CDFs or inverse probabilities by graphing a horizontal line along with the CDF and doing a calc intersect. So you can go back to that video and review that if you need to. Now, again, an F-test tests for difference in variances, or if differences in variances are going to be differences in standard deviations. But it's very non-robust with respect to the normality requirement. Both samples must come from normal distributions. Now, we talk about a procedure being robust. Well, the t-test, for example, is a very robust test with respect to the normality requirement. So if you have a distribution, it's not exactly normal, but it's kind of close. If it's fairly close, the t-distribution, or the t-test anyway, is going to work out pretty well, and the t-interval is going to be pretty close to what it really should be, even if the normality requirement that you're really supposed to have is not 100% satisfied. But if it's pretty close, you're fine. But in this case, the F-test is very, very sensitive to this, very much non-robust. So if you even have very small differences from a normal distribution, then this F-test will give you very, very poor results. So some statisticians even really avoid using this one if it's not, if we're not sure about that requirement. And so before you run this test, you should do some sort of normality test to make sure that your data comes from a normal distribution. Now, on the TI-84, remember that FPDF and FCDF functions are built in, but it does not have an inverse F function. It does have a built-in two-sample F-test, but it does not have a built-in F-interval. So some really good shortcuts for us on the 84, and a few that we were blessed with on some of the other distributions we don't have here. So the confidence interval is for, well, usually a confidence interval is for the ratio, sigma 1 over sigma 2, that is the population standard deviation over the population standard deviation for the two populations. And it turns out to be the standard deviation over the standard deviation 1 over standard deviation 2, that is sample standard deviations, times these other factors, and this is a square root of f sub alpha over 2 in the bottom and the square root of f sub alpha 1 minus alpha over 2 here. Now remember, alpha over 2 is the area to the right, and so this f sub alpha over 2 really is an inverse f, where the cumulative probability is 1 minus alpha over 2. And just like we saw in the chi-square distribution, this is kind of backwards in the sense that because you're dividing it by it here, the f sub alpha over 2 is actually going to be an area to the right, or we're going to know the probability to the right, and we're going to find that, and that's going to be the bigger number of these two. F sub alpha over 2 is going to be bigger than f of 1 minus alpha over 2. But use the right one to figure the left limit. Okay? So the lower limit here is going to be done by the right one on our picture, and our left one on our picture is the one f of 1 minus alpha over 2, and that's going to figure the right interval. So we'll take a look at this in a minute. And of course, if I multiply everything by sigma 2, this gives us an interval for sigma 1. It's some number times sigma 2, and then another number times sigma 2. So this interval gives us something about, notice that this is a little different than the intervals, say, for means or proportions, where we have a number, where we have our target one, and then it's plus or minus a certain amount. This one is basically going to be our target number multiplied by some things. So let's take a look at some example, or one example anyway. 1 year at Arizona State University, a new teaching method was attempted for an algebra class, I think, and the experimental group was taught with the new method, and 20 students from this group took a common final exam. The sample standard deviation of this group was 5.286 on this assessment. A control group was taught using the old method, and 41 students took the same final exam. The standard deviation of this sample was 7.813. Now assume that these are random samples from normally distributed populations, and remember that was important for us. We're going to perform a test of hypotheses to test for a smaller standard deviation in the experimental group. Obviously it was a slightly smaller sample, but is it statistically significantly smaller? That's what we got to find out. We're going to use a 5% significance level, or 0.05 alpha level. And we're also going to construct a 95% confidence interval for the ratio of the standard deviation. So we're going to both compute an F-test and an F-interval. So now remember that the null hypothesis is that the two standard deviations are the same, or the two variances are the same. And of course that means that the ratio of the two standard deviations is 1, and of course that means the ratio of the two variances is 1. The alternative hypothesis is, in this case, a left-tailed hypothesis that the variance of, or the standard deviation of the first sample is less than the standard deviation of the second sample. The first sample here being the ones taught with the new method, the experimental group. Now notice that corresponds to saying sigma 1 over sigma 2 is less than 1. And so S1 over S2 is going to have an F distribution with 19 and 40 degrees of freedom. Remember, we had 20 students, so subtract 1, that's 19 in the first group, and the second group had 41 students, subtract 1, that's our 40 degrees of freedom. So 19 and 40 degrees of freedom. So here we have it worked out. I actually have this worked out 3 different ways. The first way, I'm going to graph the PDF and then shade the appropriate area and compute it. So first of all, I'm going to compute the F statistic. Okay, and so I do the ratio here of the two S's and then square it, because I want the ratio of the two variances, or square them each and then divide, and I get 0.457739, etc. Okay, I'm going to take that and store that as F, so I don't have to type all these digits in again later. So that's my F statistic. Now I go ahead and graph. I'm going to graph this PDF, and I don't have the y equals screen up here for some reason, but it's going to be, you can see it right here at the top of this third screen. It's F PDF of x, 19, 20, and the window I chose was from 0 to 4 on x and negative 0.2 to 1.2 on y. Then I choose, so that's going to give me this graph. And then I want to shade the right part. Now remember, to shade the right part and compute an area, what we want to do is we want to do a numerical integral and shade it. So that's calc, so second trace, and then it's the last one at the bottom, the one with the integral sign. And so it asks me for a lower limit, which is going to be 0. That's as far to the left as it goes, is 0. And then enter. And the upper limit, I could either type in all these numbers here, or I can just type in F, since I've already stored it as F. So I just typed in F, and hit enter, and it comes back with the right region shaded. It has the graph of the PDF, it has the area shaded that we want, and it has the probability, which is our p-value, 0.035 roughly. Now, as always, it's really easier if we don't shade the area. It's visually nice and it gives us a good visual of what's going on, but it's easier if we just compute the area without shading it, and we can do that with an FCDF since we have that built in. It's a lot easier. So we can just go to the home screen here. I've already computed F, you see here, and so I just do FCDF, And again, you get that by doing going to distributions. So second variables gives you distributions, find FCDF, and we want to calculate the area from 0 up to this F value of 0.45 whatever. So where I have the F here, you could have just typed in that number. Okay, but I've already figured it out as F, or you could have just said previous answer since it was the previous answer. And then go 19 and 40 degrees of freedom, and we get our p-value here, which is the same p-value that we saw there. In this particular case, probably the easiest way to do this is with the built-in two-sample F-test. So third way to do it is with the two-sample F-test, and that's the easiest way to do it of all. We go to two-sample F-test. This one's done from statistics. We give it S1, which is 5.286, N1, which is 20, S2 is 7.813, N2 is 41, and we want sigma 1 to be less than sigma 2 for the alternative hypothesis, so we highlight that and calculate it, and it comes up with this. Notice it comes up with the F statistic, which is exactly what we came up with before, the 0.4577, etc. It comes up with the same p-value that we computed before, and it comes back and reminds us what our S1 and S2 and N1 and N2 are. Now, also, if I had two sets of data, I could put those in as, say, list 1 and list 2, and then chosen data here instead of stats, and then, list 1 I could put L1 and list 2 L2, and then go ahead and do a calculation that way, and it would return these summary statistics for that, which are very useful to have. So the main thing, of course, to conclusion of a hypothesis test is to look at the p-value. The p-value is 0.035, and that is less than 0.05, which is alpha. So p is less than alpha, then we reject the null hypothesis in favor of the alternative. So we see there is enough evidence to conclude that the experimental group had a smaller standard deviation on the final exam than the control group. Now, how about a confidence interval? Now, again, if I were just doing this hypothesis test, probably I would just go straight to two-sample F-test, and you just got these last two screens here to deal with. The first one where you enter your data, the second one, hit enter, and it tells you the outputs. And probably I would just do it that way. You could also select draw instead, and basically you're going to come out with this picture over here where it's drawn and shaded, and it'll, instead of this saying integral whatever, it'll have P equals this, and it'll have F equals the 0.4577. So it'll give you both F and P if you do that way and draw it on the PDF. Now, what about a confidence interval? Well, the hypothesis test is built in the 84, so we could use that, but there is no confidence interval built in. Okay, so we need to look at that. So to do that, I need to do, for confidence intervals, I'm going to need some inverse F's. Well, we don't have an inverse F function built in, but we do have an FCDF. So what I want to do is graph the FCDF. So notice I've toggled off the FPDF. I put in the formula for FCDF going from 0, which is all the way to the left, up to X, 19 and 40 degrees of freedom. And then I'm going to need intersections of that with 0.25 and 0.975. Now, where did those things come from? So we have a 95% confidence interval. That's our 1 minus alpha. So our alpha is 5%, 0.05. And this is wrong. Okay, I'll just fix this. Almost right. The right endpoint is correct, but the left endpoint is not. It won't hurt us to see this. So we have our 0.05 is the interval. We want half of that is our probability. So we want 0.025 for the left, and then 1 minus that for the right, which is 0.975. I got the 0.975 right, but I didn't get the 0.25 right. I think I have this still in here. Good. So I need 0.025, and we'll make this correction. Okay. So now I can graph that. This is going to take just a second, but it's going to graph the CDF along with these two horizontal lines. And the one that's messed up is the one on the left, which is actually which will end up generating our upper limit on our interval. So I need to get rid of I need to replace those two things and that one actually. Okay, so this is going to take just a minute to do. So let's look at the other end. What we did is, notice we have the horizontal line at 0.975 and our CDF. We just did a calc intersection between those two and found the point X, and of course Y is 0.975. So when I come out of that, back to the home screen, I type X, and then we get our value. Then here's the formula for the what we have here. So that's on the right end. That's F sub alpha over 2. This is going to be involved in finding the left or lower endpoint. So I need to do S1 divided by parentheses S2 times the square root of this value that we just came back. So second answer, or X, and then store that as L, and that's my lower endpoint. Okay, now to get my upper endpoint, I need to go back here and let's do this. So let's go back here and show everybody what we have. Okay, so there's our screen, and now we want to do a calc intersection, number 5, and the first curve is our CDF, that's good. Our second curve is 0.025, that's good, and I'm going to guess 0.3, and let's see how that comes out. I could have just arrowed over and made a guess. Okay, and so we get 0.4, about 0.43 roughly. So now notice that if I quit this, okay, and just type X, that's the same value that we just did. So now to find that was on the left end here, so that's going to be used to find my right thing. So I need to do S1, which was 5.286, divided by parentheses S2, which is 7.813, times the square root of what we just came up with, which was X. Okay, close the square root, close the parentheses around the denominator, and I'm going to store that as U for upper. Actually, I don't have to really, I can just write it down. But in case I want to get back to it later, there it is. Okay, so it means I need to change these. I need to change the upper one to 1.0334. So that gives me my interval. So my interval for the ratio of the standard deviations of the populations, that's our confidence interval. We're 95% confident that the ratio here is between 0.4684 and 1.0334. Or if we do a confidence interval just for sigma 1, it's between 0.4684 times sigma 2 and 1.0334 times sigma 2. Okay, so that gives you an example of how you go about doing an F interval. So there's that concludes our introduction to these topics.